We're going to study the natural or source-free response of an RC circuit. If we have a circuit with two resistors and a capacitor and a source connected to it for a long time, we're going to denote this time as t less than 0. The energy flows out of the source into the network, and the energy is transferred to the capacitor in the form of a voltage in the electric field. If the capacitor is fully charged, then it turns into an open circuit, so no more current flows into the branch with the resistor R1 and the capacitor. If the source gets disconnected or a switch is open so that the source is disconnected from the circuit, no current flows into the network. We're going to denote this instant of time as t equals 0. The energy on the capacitor will remain the same, since energy cannot be dissipated in 0 time. Now we're going to take a look at the time after the switch is open, and we're going to denote this time as t greater than 0. The capacitor remains connected to the resistor network, and the energy is going to be dissipated by this resistor network. The energy dissipation can be modeled by the following equation. B sub c of t is equal to a e to the minus t over tau for t greater than 0, where tau is known as the time constant. Tau then is equal to the equivalent resistance times the equivalent capacitance of the network. By convention, the circuit response would fall to 0 in phi time constant, and this is known as the transient response. Now that we have the equation for the natural or source-free response of an RC circuit, if we want to have a graphical representation of these equations for values of t greater than 0, we can create a table and we can assign values of time multiples of the time constant. So if we assign t equals 0, we're going to get a voltage B sub c equal to a times the exponential to 0, that is going to be equal to 1 times a. If we assign t equal to 1 time constant, then V sub c of t is going to be a times exponential to the minus 1, that is equal to 0.368 times a. If we assign t equal to 2 time constant, then V sub c is going to be equal to a times e to the minus 2, and this is equal to 0.135 times a. If we assign t equal to 3 times constant, then V sub c is going to be equal to a e to the minus 3, that is equal to 0.05 times a. If we assign t equal to 4 times constant, then V sub c is going to be equal to 8 e to the minus 4, equal to 0.018 times a. If we assign t equal to 5 times constant, V sub c of t is going to be equal to a e to the minus 5, that is equal to 0.007 times a. By convention, at 5 times constant, V sub c of t is going to 0. And then with this point, we can sketch the response, the graphical response of B sub c of t for t greater than 0, and we can see that it looks like a decaying exponential.